Hi, so thanks for tuning in again. We are going over Chapter 1, Section 5, Matter, the Stuff of Chemistry. So we're going to get into a little more detail about mass and volume, the two main components of matter, right? The two major characteristics. So mass is anything that takes up space that can be placed on a scale and weighed. It weighs something. You remember that definition from very early on in this course. So mass is a measure of the amount of material in an object. Make sure you make some flashcards and you get familiar with this jargon, okay? So the amount of material in an object. And a common unit that we use to measure the mass of a substance is a gram, okay? So you need to have that unit, right? That's a measurement that's involved in your measurement. You can't just have a number. I mean, whenever instead of talking about grams and using the metric unit, we use pounds, right? You wouldn't say I weigh 100. 100 what? Well, pounds. So gram is the unit that you're using for mass. Okay, make sure you understand that. That's the very basis. The weight of an object is determined by the pull of gravity on that object. Okay, so that's why weight changes. Your weight on Earth versus your weight on the moon is going to change because of the pull of gravity. That's different, right? But your mass is not going to change. That's what the difference is. On the tallest mountain, like anywhere in the world, mostly you have the same weight, but, you might have a slightly different pull on the tallest mountain, maybe a little less pull, but just in general, everywhere in the world, you have a similar weight, but you have the same mass, no matter where you are, the Earth, the moon, so on and so forth. Okay. All right. So when you think about that and how there's less gravitational pull and less weight, that's why you have the astronaut floating around whenever they're on the moon, right? Okay. So you probably understand the differences between those things. And volume is the other major component or major distinction of matter. And that's the three-dimensional measure of the space that's occupied by matter. In labs, volumes are usually measured with graduated cylinders or pipettes, or a multi-channel pipette, for example, or a handheld pipette that you may be familiar with looking at. If not, I can show y'all an example in class, perhaps. But the unit that we typically use in a lab and what we call it in a lab is a milliliter. Often in research, you'll order something like a lyophilized toxin or something of the sort, or a lyophilized adjuvant, something that'll stimulate the immune response, and you resuspend that in a liquid in a 1 milliliter amount. Oftentimes, you'll have 1 mg per mil because you add 1 milliliter of liquid to that powder that you ordered. So often we use milliliters in labs, and that keeps everything relatively simple. In a clinical setting, you use calibrated syringes. So a lot of times in allied health, you'll be using a syringe with the little markings like you see here. In a typical unit in a clinical setting, you might refer to, I'm not sure why this slide is spaced out this way, but you're typically going to use the cubic centimeter. So 1 milliliter equals 1 milliliter equals 1 cubic centimeter, right? Okay. All right, so that equals 1 cubic centimeter. All right. But if you are, a person who is wanting to sort of be able to go back and forth, And if you need to give your child, you know, a certain amount of cough syrup, for example, in your kitchen jargon, you might refer to teaspoons rather than mils. And being able to go back and forth between those two ways of measuring in units between, you know, household names and the metric system can be an asset. For example, 5 mils is a teaspoon, right? And if you relate both mass and volume, then you have an understanding of density. Okay, that's a comparison of a substance mass to its volume. So basically, this is a ratio, and it can even be considered a conversion factor. So this is going to be D equals M over V. And sometimes it's easy to remember these things with, you know, mnemonic type devices or little tricks. And, you know, Department of Motor Vehicles, DMV, that's a way that I've always remembered this equation, but I think this is probably on your best friend, so you don't have to memorize it. But it's always good to know these things, because density, you have to understand what it is, right? It is a comparison of a substance's mass to its volume, right? So 1 gram of water has a mass of 1 milliliter, okay? So that basically means, if you would write this out, that D equals 1 gram H2O over 1 mil H2O. So this unit of grams that we use when we're talking about mass, and here when we're talking about the volume, right? So we have mass over volume equals density. So that density of water is going to be in what units? Grams per mil. So mass over volume, and it's 1. All right, 1.00, the density of water. Because the density is constant at a certain temperature, right? If you change a temperature, you change the state of matter. So the density is dependent or on temperature. But most of the time, the density is going to stay constant if the temperature is constant. And so we can use the density as a conversion factor in some of the problems that you're going to be given to determine either mass or volume of a substance. Depends on what you're given, and you can plug in what you're given and define what you require, what you're being asked in order to find your answer. Just solve the equation, plug it in. All right. So in this example right here, speaking of density, with water, you can really easily tell whether something is more or less dense by this simple experiment, whether or not something floats or sinks relative to water. So you have this beaker of water here, and you have this piece of wood. You know, most types of wood are less dense than water, and so they're going to float, okay? Whereas you have this wood that is more dense than water, and it sinks. All right, I mean this piece of metal right here. I don't know if I said wood again. So this is kind of a simple experiment that maybe you've done before. All right, so it's all about how dense those atoms are. Okay, so how dense the atoms are. And that depends on the temperature, because it depends on the state of the matter. All right. So you're going to hear that again and again, and that repetition, I think, is going to help you. Specific gravity. All right. So this is when a liquid density often is measured with respect to water. All right. So water, we know that the density of water is 1 gram per mil, 1 gram per 1 mil. Okay. So that's equivalent. at 4 degrees Celsius and close to that value at body temperature. Okay, so 4 degrees Celsius, that's like the temperature of your refrigerator. Okay, and it's close to that at your body temperature. So the ratio of the density of a sample to the density of water is called the specific gravity. And so this equation can be written out this way. Specific gravity equals the density of a sample over the density of water, right? So you see this pretty obvious relationship, and that is specific gravity. And specific gravity doesn't have a unit. Why? Because you have grams per mil over grams per mil. This cancels out. This is a ratio, right? You can measure specific gravity with something called a refractometer. You'll see these in marine labs, and that's helpful whenever you're determining salinity. That can just be something that's one tool that you can use to make sure that the water for your animals is adjusted to what it should be. A refractometer is often used in a clinical setting during urine analysis. So you're gonna have problems that can probably be solved, or would in an applicable setting be solved with a refractometer. But make sure you understand this definition. Perhaps I'll bring one to class. So we mentioned already that we're talking about density, and we're talking about specific gravity, but what causes density to change? And I already said it before several times, so you should remember now. Density can change whenever what changes? Temperature, right? It's constant. Density is constant at the same temperature, but if the temperature changes, the density changes. The state of matter can change, okay? So start to be familiar with this relationship. All right, so we measure temperature with what? And you know that that determines the degree of hotness or coldness. Notice I said degree, so we're going to talk about degrees. And we measure this with a thermometer. There used to be, mercury-based thermometers. There's electronic temperature probes. We're all very familiar with thermometers, especially in the past few years. In the United States, we use Fahrenheit. The rest of the world uses Celsius. And there's more than that. There's also Kelvin. Okay, so when we talked about the metric unit, the SI units before that we're going to be using, basically we're talking about the metric system, so on and so forth. Kelvin is the SI unit for temperature, okay? So think metric. It's really important to understand when somebody says, what temperature it is, to pay attention to the unit that they use, because using this chart here, you can see if you just say a number, that's really going to throw people off in other parts of the world. Take, for instance, Fahrenheit, 98.6 Fahrenheit. In the US, we know that that is normal body temperature. But if you just say, let's say you heard somebody from England say, oh, my temperature is 37 degrees. Well, that wouldn't make any sense at all. How could they be so cold, right? It's really important to be familiar with these units, right? Just as we were talking about how you can't just say a number for mass. The unit needs to be there. Grams, or is it pounds? And if it's grams, are you talking about kilograms, milligrams? You have these prefixes to pay attention to. So always remember your units, or there is no meaning. They don't convey and they don't make sense. All right. And then you have Kelvin over here. So there's a really obvious relationship between Celsius and Kelvin. All right. The two scales are offset by 273 degrees. All right. So that's easy math. Okay. You can see if you look back here, it's just a difference of 273 degrees. All right, between here and here, here and here. All right, if we're looking at the freezing points, really obvious. But if you are looking from Celsius to Fahrenheit, it's not so easy, right? You see that here the difference is 32. Here the difference gets a little bigger. Here the difference is even larger. So that's going to be a more complicated formula. So if you have Celsius, then you're going to take, or if you want to know Celsius and you're given Fahrenheit, you have to subtract 32 degrees from that. And then you take that and you're going to multiply by 1 degree Celsius over 1.8 degrees Fahrenheit. Okay, and you have your formula here for figuring out degrees in Fahrenheit if you're given Celsius. And one of the most important things about temperature is body temperature, something that we were just now talking about, right? So our body temperature is 98.6. It varies throughout the day for everyone, and it's slightly different for everyone. But in general, 98.6 is homeostasis. Okay, that's the best temperature for all of your cells, your organelles, your organs to function at. Or 37 degrees Celsius. So remember that. If you rise above 40 degrees Celsius, or notice the difference here, the changes, and 104 Fahrenheit, that's hypothermia, that's a fever. So, for example, you have an infection, and that induces your body and your cells to produce all of these proteins. Some of them are called pyrogens, right? Like heat, like fire. And they cause your temperature to be elevated, and you can have convulsions, double vision, coma, brain damage. That's why what you have to do when somebody has hypothermia, a fever, you have to get that person much cooler very quickly, like put them in an ice bath. And if the body temperature drops below 35 degrees Celsius, that's hypothermia. That exists. That happens sometimes with certain metabolic disorders. Whenever food isn't broken down properly, energy is not produced properly, and you can have a low body temperature, and that can cause an irregular heartbeat and a slow breathing rate, and it can be fatal very quickly. And so we're talking about temperature and heat. But what is heat? It's energy, and energy is heat. All right? So energy is the capacity to do work, supply heat, like when you exercise. So stored energy is potential energy, okay? So that burger that you're about to eat, it has potential energy, all right? And then that energy is transferred. So the biker at the top of the hill that hasn't started to move yet, they have a lot of potential energy. And then when they start moving, that exercise starts, that transfers to kinetic energy, okay? So you have all these forms of energy, and it's not created or destroyed. You remember hearing that before? Conservation of matter, right? So this is the conservation of energy. Okay, these things are not created or destroyed. All right, that's powerful. And so the SI unit we were talking about for temperature is what? Kelvin. And the SI unit for energy is the joule. A joule, okay? So make sure you memorize all of these units and what they mean, and you understand their quantity and qualities. So a calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. And this is going to be important in regards to body temperature. And you'll see that in just the next slide or the next couple of slides. So a nutritional calorie that you're going to see on your food package is 1,000 times greater than the calorie that's mentioned in this definition, which is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So that's Celsius, it's not Kelvin, even though we're talking, we're just talking about SI units, okay? So that's not Kelvin. All right, so just remember that calorie that you're used to on your package is calorie with the capital C, and that's 1,000 times larger than calorie with a little c. Okay, that's easy to remember. All right, big C, bigger, 1,000 times larger. You're going to have some problems to work with that. So whenever I was telling you just now that calories and energy were going to have a lot to do with maintaining your body temperature, that's all because of specific heat. Okay, heat and specific heat. Okay, just in general, you know that heat is kinetic energy. It's a transfer of energy from a warmer body to a colder one. Okay, just like that's happening whenever you have a glass of ice and you decide to add water to that ice. Okay, so the warmth of that water is transferred to that ice and the ice melts. So you see that happening, all right? You see that taking place, and every substance has the ability to absorb or lose heat. Just as when you're getting into a cold car and you're, you are the warmer body. When you get into a car, you feel colder at first. You're transferring heat into the car, okay, on a cold winter's day. So specific heat capacity, or the specific heat of a substance, is the amount of heat needed to raise the temperature of 1 gram of that substance by 1 degrees Celsius. So sounds familiar to a definition that we were just talking about 30 seconds ago, right? On the previous slide when we were talking about calories. Okay, so specific heat equals heat over grams times the change in T. Okay, so metals have a low specific heat value. All right, it's easy and it requires less energy for those metals to change temperature. Okay, and it takes more energy for water to change temperature because it has a higher specific heat. And that's good because your body is made mostly of water, right? So most of what you are made of has a very high specific heat, and you don't want fluctuations in your body temperature, right? So that's good. Prevents large fluctuations in your body temperature because you're made of water, right? You know that. Okay. And so it takes a lot of energy to change that specific heat, that temperature of your body relative to metals. And you have this chart here, which gives you a summary of the specific heat of all of these substances. So you see water there. You've got 1 calorie per grams degrees Celsius, because that's what those are your units. If you're looking at the formula on the previous slides for the human body, see that it's close to water. And you have aluminum here, okay? And you have some metals down here. So it's harder to change the temperature of aluminum And so you notice, like, when you take something out of the oven, you can a lot of times touch the aluminum still quickly, or after you've just recently put that in the oven, you can still touch the aluminum and it doesn't burn you. And so sometimes, to prevent the crust on a pie, if you're a baker, from burning, you can line that metal pan with aluminum, right? Because it's going to take more energy to change that specific heat, to change that temperature, right? So prevent your pie crust from burning. All right, the states of matter, the physical form in which matter exists. We talked about the three different examples: solid, liquid, and gas. But we didn't talk about the properties of those. So what does that mean? So basically, just think about that. Do you remember what makes something on a particle level a solid, liquid, or gas? And it's written for you right here, and we have our trusty example of water, ice, and water vapor. So here the particles are so tight in a solid that they're barely moving, okay? So this contrasts to liquid, where they're a little more free, they're flowing. And then whenever you have a gas, those particles are so disordered, they're, hitting the sides of whatever container they're in, they're bumping into each other like bumper cars at a fairground. And those are the differences, those are the properties of the states of matter: solid, liquid, and gas. Okay. And so here you have some definitions of that written out for you, because you know that the state of matter has a relationship to density, and this is all a factor, or this is all related to temperature, right? So you can clearly see that in this example, right? So you can see why this chapter is organized in this way, where you have density, states of matter, and temperature. Okay, so states of matter, the particles in a solid or in an orderly arrangement, they're tight, they're barely moving, and that's whenever you have a solid, there's a definite shape, there is a volume. Where when you have a liquid, the particles in the liquid, they're moving around, they're fluid, they're flowing, and it has a definite volume, but takes the shape of its container. So, right, it doesn't, no, the shape is going to change depending on what the container is, right? Whether it's a beaker or it's a jug, the shape can change. In a gas, the particles are moving all over the place. They're not in order. It's disorder. They bump into each other, so there's no definite shape or volume, and it expands to fill the container in which it's placed, right? Just keeps moving. All right, so here is your summary in this nice little table that we've got here, with the property of a substance, whether it's a solid, liquid, or gas, and its shape, volume, kinetic energy, positioning of the particles, and attraction between the particles. You should probably review that and know that for your test. Measuring matter is going to be on the next pre-lecture video. So right now we're going to go over some problems. All right. Here. Okay. So we're going to go over the odd problems. We're going to do the even ones in class. So based on your experience, based on what you know and what you've done and what you've seen, is each of the following more or less dense than liquid water? A, vegetable oil. What happens if you pour that oil that you're going to fry something in over water? It's going to float. So that means what? It is less dense. Remember? Like the wood in the water. a piece of gold jewelry. Remember that metal in the slide? Okay, that's going to be more dense. And what about a cork? You drop your cork in some water in the bathtub. It's going to float. So that is less dense. So less, more than less. Okay. 1.37. Calculate the grams of sugar present in a 355 ml can of soda. Assume mostly sugar and water. If the water in the can weighs 355 grams and the density of the soda is 1.11 grams per ml. All right, so we have the total volume. The total volume is 355 mils of soda. All right, let's write our equation here. It always helps to see your equation to start off with. So D equals M over V, Department of Motor Vehicles. All right, so we have our density. I told you, you just see what you have and then recognize what you need to find out and set up your equation, plug it all in. Okay, so you have 355 mils, all right, times 355 mils equals 1.11, let's do like this, grams over 1 mil, because you have this. Okay, so, all right, let's see. So we're going to solve for x, right? Oops, that's sort of messy. Let me erase this. All right, 355 mils times, I said times, I don't know why I wrote an equal sign, 1.11 grams over 1 mil, right? So you see what you were given, all right? You have this 355 mil can of soda, okay? You have the density of the soda, all right? And so now we're just gonna solve for x. All right, so 355 times 1.11 grams and get your answer. And how many significant figures we're going to use? Your answer is 394 grams of soda. All right, so here is your answer. And we're going to move on to 1.39. Make this a little bigger for you guys. Allied health. Okay, I like these applicable problems. Oh. A person's urine has a specific gravity of 1.002. All right. 1.39. A person's urine has a specific gravity of 1.002. Is this person more likely dehydrated or overhydrated? Okay, so you remember, all right, so we're looking at the specific gravity here of urine versus water, okay? All right, so that's what specific gravity is. We're given urine in this problem versus water. And we're looking for what we're given in the problem here. And so you have all of your information there. And you can write this. So 1.002, your sample over water, and you have this ratio, cancels out. So you know that's 1.002. And it's important to understand that if somebody is dehydrated, there's going to be more particles dissolved in their urine. It's going to be heavier. Okay, so the higher this number is, the more dehydrated that person is. All right, and it helps you to kind of understand a range. All right, a lot of times, so 1.002, that's pretty close to 1. That's pretty close to water, right? For the specific gravity. However, 1.002 is pretty close to the normal range. This person is likely, though, more overhydrated compared to dehydrated. Okay. Whereas if that person's specific gravity for their urine was, I think about 1.030, in that case, that person would be very overhydrated, actually. All right. So if it's, I mean, that would be dehydrated, right? So the higher the number is, the more dehydrated that person is. All right. So the answer here at 1.002 is they're more overhydrated, but they're really kind of almost in normal range. Okay, 1.41, allied health. A family visiting Europe goes to the hospital because their child is sick. The child has a temperature of 40.3 degrees Celsius. Calculate the temperature in degrees Fahrenheit. All right, so you know you're going to have to use one of those formulas you've seen on the last slides. All right, 1.41. So we are given Celsius, and we need to know Fahrenheit. So that equation, if you flip back, is F over 1.8 degrees Fahrenheit over 1 degree Celsius. Okay, oop, not done yet. Okay, times, because we're going to cancel out, plus 32 degrees Fahrenheit. And that's going to give us degrees Fahrenheit. All right, so go ahead and plug in your Celsius in your calculator, and you're going to get the readout that you'd probably get on your thermometer, be 104.5. Let's see, get this. But really, we could say 105 if we're going to go with our significant figures, but with temperatures, it's really okay to say 104.5 and do your rounding here. Degrees Fahrenheit, degrees Fahrenheit. Okay, so this is acceptable for this answer. All right, so 1.43. Discuss the different type of energy present in a snack before, while, and after you eat it. So we're talking about a transfer of energy here, okay? So before you eat, before eating, and I mentioned a burger in the example, that is potential energy. And then while eating, you're chewing and some of it's being swallowed and broken down. This is going to be a mixture, right? And as you continue on, and after you eat, after eating, you're ready to use those nutrients, that energy that you got, and that is now kinetic energy. All right, that's energy in motion. So 1.45, allied health. I like these examples, y'all. A defibrillator delivers about 360 joules per shock. Calculate the number of calories. Okay, so you need to remember that 1 calorie, if you read your book, you remember, so all you need to read the book, is 4.184 joules. So, okay, you will write your equation. You have 360 joules. Okay, you're going to need to use your conversion factor. So you want calories, so you're going to have 1 calorie over your 4.184 joules. So that joules are going to cancel out. You're going to get calories of 86. And that's your answer. All right. We've only got a few more. 2 warehouses have a space available for storage. One's made of brick, the other one is pine, a soft wood. Which one will keep its contents cooler on a 90-degree Fahrenheit hot summer Louisiana day? Support your answer. All right. So the specific heat of brick, so specific heat for brick is about 0.20 calories per gram degree Celsius. And for most wood, or lots of wood, it's about 0.34 calories per gram degree Celsius. So you see that you have a higher specific heat for wood. So basically, it's going to take more energy to change this temperature, and you're going to keep your contents cooler in the storage that is in the storage warehouse that is made of wood. So the wood is going to keep cooler. So you have to remember why, and that's because it takes more energy to raise 1 gram of material by 1 degree Celsius. So you need more energy to have more heat. So basically, it's going to take more for the wood to change temperatures. Basically, so that's better climate control. That's where you're going to store your things. All right. And 1.49 indicate if each of the following describes a solid, liquid, or a gas. Okay, 8. The state of matter has no definite volume or shape. Okay, so no volume, no shape. You know that is a gas because we just went over those definitions. The particles in this state of matter are really rigidly fixed in place, and you know that is a solid. All right, that's it. Thank you for tuning in.